This is lecture 17 in BBSP 610. We'll be discussing correlation. And before I dive into the discussion on correlation, I wanted to give a general overview of just how you approach a given data set and you don't know what test to use on it. That's one of the most common questions I get in this class is, Eric, you've taught us all these methods. How do I know which task to use in a specific situation? And so I was going to give a brief overview of that question. We'll discuss it in more detail later. But just to give some context for correlation, but in one of the most common problems in statistics is you want to consider the relationship between two variables. And oftentimes we hope that one variable will predict or explain the other variable. That if we give a placebo and an active drug to two groups and hope that the active drug results in greater pain relief than the placebo, then the type of drug that people get would be what's known as a predictor variable, and pain relief would be known as what is a response variable. In general, a variable that's used to predict the other variable is known as a predictor variable, or sometimes an independent variable or an input variable. The variable that we're trying to predict would be a response variable or sometimes an outcome or dependent variable. And two questions we may want to answer about these types of relationships is, first of all, is the observed relationship real? Is it a stronger relationship than we would expect to observe due to chance? And how strong is this relationship? And we can answer the first question using hypothesis testing. We can answer the second question using confidence intervals. And the appropriate test to use when you want to know if two variables are related to one another depends on what type of variable. As you'll recall, we've had in the two main types of variables are categorical variables that can assume a certain number of discrete values, or quantitative variables and numeric variables. And if we want to look at the association between two categorical variables, examples of this would be, is type of drug you get, active drug versus placebo, related to pain relief, or is smoking related to lung cancer, or is race related to the risk of developing chronic pain after a car accident. In all these cases, both variables are categorical. They assume only one of a set of possible values. In cases like this, you would use chi-square tests or proportions tests or Fisher's exact test to test the null hypothesis of no association between the two categorical variables. If you have one quantitative variable or one categorical variable, or one quantitative variable, one categorical variable, say that we give some of our mice a hormone treatment and some of them a placebo, and we want to see if there's a difference in the weight between the two groups. Or say we want to know if smoking affects a baby's birth weight, or if two different tumor types have different gene expressions. In both of these cases, we have one quantitative variable and one categorical variable. The growth hormone is either treatment or placebo, but the mouse's weight is quantitative. Likewise, smoking is either you smoke or you don't. That's categorical, but the baby's birth weight is quantitative. In cases like that, you would use a t-test to test the null hypothesis of no difference between the groups. If the assumptions of the t-tests are satisfied, you can use other non-parametric tests, such as bootstrapping, which is something I no longer cover in this class, but I'll just mention in passing this exists, particularly if the assumptions of a t-test are violated. But for the rest of today and for the next several lectures, we're going to be considering the case of two quantitative variables. Say we want to know, does pulse rate change with respect to age? Or is there an association between alcohol consumption, HDL, bad cholesterol? or is there a relationship between gene expression and time to metastasis in cancer patients? In this case, you have one quantitative variable and you want to see if it's related to another quantitative variable. And so for the next several lectures, we'll be discussing methods and tests to see if such associations are real, and also describe how strong such an association might be. The first step when you want to look at the association between two quantitative variables, in most cases in statistics it's advantageous to plot the data. So a simple way to do that is to create what's called a scatter plot. This is a data set that's built into R, it's called CAR. The idea is to try to predict how long a car travels between when you hit the brakes and when it comes to a complete stop based on its speed at the time you hit the brakes. And you would hypothesize that the faster the car is going, the longer it's going to take to stop. And if you look at this scatter plot, it looks like the appearance of the data is consistent with that hypothesis. The command in R to do this type of scatter plot is called plot. Like I said, this data set's built into R if you want to try this example yourself. This data frame in R called cars has two columns, one called speed and one called distance. So I attach the cars data frame so that I can reference the columns one by one and then say plot, speed, comma, distance, and then add labels for the graph. In general, in R, if you say plot x comma y, it'll draw a scatter plot of y versus x. And you can and should use the parameters xlab, ylab, and main to label the graph, as we did when we created our graphs previously. The syntax exactly the same for the other plotting functions that we've talked about before. And when you draw a scatter plot, the convention is the predictor variable goes on the x-axis and the response variable goes on the y-axis. There's nothing magic about that, but that's the way most people do it, so I recommend that you do the same, or eyebrows might be raised by reviewers. And you also have to consider the scale on the x-axis and y-axis. R will choose the x-axis and y-axis range for you automatically. We usually do a pretty good job of it, but sometimes you might have to make some tweaks. And you also want to consider things when you draw graphs, particularly for publication, the font, the size, the color, things like that, to make it easy to read and visually appealing. I won't go into the details of that, just mention that it's something to consider. I will note that when drawing scatter plots, it's important to choose the axis labels or the axis scales appropriately, among other things. This graph here shows the death rates from heart attacks, and I believe this is the United States from the period 2000 to 2006. If I draw the graph the way you see it on this slide, you might think that it's been relatively level over time, but if I draw it on the next slide, you can see it's actually been decreasing over time, not by a huge amount, but by a certain degree. In the previous plot, the y-axis scale was too large, so it looked flat, even though there was a slight trend downward. If you do a more appropriate axis scale, then this downward trend is visible. Like I said, if you do these plots in R, it will do this automatically and generally does a pretty good job, but something to think about when you draw graphs in general. And the things that you want to look at when you look at a scatter plot is the overall pattern. Is the association roughly linear? Is it curvilinear? It looks kind of curved. Do you see gaps, clusters, things like that? Do you see evidence of outliers or other data points that don't see the pattern? Is the overall association strong or weak? These types of questions. I'll discuss this in a little more detail later on. Strong or weak means that, like, if you know X, can you predict Y with a high degree of accuracy, or is there very little association between X and Y? So, some terminology is to be familiar with positive and negative association. If x increases, then y also increases. You say that's a positive association. If y increases, or if x increases, then y decreases. That's what's known as a negative association. It's also possible there's no association or there's a nonlinear association if you have like a U-shaped association where for a while y decreases as x increases, but later on y increases for larger values of x. That would be neither a positive nor a negative association. That would just be, but there would be some association. It would be, or just isn't a simple term for it in that case. So this graph here shows some examples of linear associations. The upper left panel, there's no association at all between x and y. The second panel, there's a positive association. You can see that y is more likely to be large if x is large. Y is more likely to be small if x is small. The third panel, there's a strong positive association. There's almost a one-to-one correspondence between x and y, that x increases as y increases. Panel 4, there's possibly a very slight negative association, but if it exists at all, it's weak. Number 5 has a more robust negative association, and panel 6 is an almost perfect negative association. If you know x, you can predict y with almost 100% accuracy. At any rate, we'll introduce our next statistic now, which is called correlation, and it measures the strength and direction of the linear relationship between two quantitative variables. That's the formula for how you calculate it. In practice, you'll use Excel or R or your favorite statistical package, so you don't need to remember that formula, but there it is if you ever need it. The properties of the correlation statistic R is that's always between -1 and 1. If R is equal to 1, that implies a perfect positive linear association. -1 implies a perfect negative linear association. In general, if R is positive, then the association is positive. If R is negative, then there's a negative association. R 0 implies there's no linear association. It doesn't imply there's no association at all, as I'll show here in a minute, but if as an association exists, it's a nonlinear association. So, going back to the graph I showed earlier, here's the correlation values for each of these plots. The first panel, there's no association, so the correlation is 0. Panel 2, there's a positive association. Panel 3, there's a very strong positive association. Get R equals 0.9. Panel 4, there's a weak negative association. You get R equals -0.3. Panel 5 has a stronger negative association, and panel 6 has an almost perfect negative association, which is why we get a correlation value of almost -1. Some other properties of R is that the correlation of x with y is equal to the correlation of y with x. X and y are interchangeable when you calculate correlation. It has no units. If you go through the math, the units cancel. It's just an arbitrary scale between -1 and 1. And R says nothing about causation. I've hopefully screamed about that enough already in this class, but just because a child's test scores increases when their shoe size increases, that doesn't mean big feet cause better test scores. It means that age implies both bigger feet and better test scores. And as I said before, R measures only the linear association between x and y, that this graph here has a U-shaped association between x and y, and if you calculate R in this case, it's exactly equal to 0, even though there's a very strong association between x and y. In general, you wouldn't want to use R to measure the strength of a U-shaped association. A classic example of this would be the association between alcohol consumption and HDL, that if you consume a small amount of alcohol, it's associated with lower HDL levels, but if you consume a larger amount of alcohol, then your HDL levels start to go up. If you calculate the correlation, it may be very close to zero, even though an association does exist. Additional properties of R is that R is not robust. A single outlier can greatly skew your value of R, and it's also not the same thing as the slope between x and y. We'll see in a future lecture that there is a relationship between R and the slope, but R is not the slope. And just to illustrate that R doesn't perfectly describe the association between x and y, here's several plots that have an R of 0.7, even though they look quite different from one another. The first example is a roughly linear association with a bit of noise. The second example is a perfect linear association, but one outlier reduces the value of R from 1 to 0.7. Example 3 is a curvilinear association, but still gives an R of 0.7. Examples 4 and 5, it looks like there might be two different groups. And then example 6 is just kind of a noisy association. All of these give you an R of 0.7. So just knowing the value of R won't give you the precise nature of the relationship, but it will give you some idea of the strength of the association between x and y. Main takeaway from this graph is that it's always a good idea to graph the data when you want to evaluate the association between x and y, rather than just mindlessly calculating R and say the association is strong or weak. In particular, as I said before, R is extremely sensitive to outliers, so even a small number of outliers can have a huge effect on the graph. Quick note on terminology that if you want to be precise, the term correlation should only be applied to quantitative variables. That is technically not correct to say there's a strong correlation between ethnicity and obesity rates, because ethnicity is categorical, and if you dichotomize obesity, that's categorical as well. But people sometimes do, and it's not something I'm going to be strict about in this class, but it's something to keep in mind. If you're talking about categorical variables, it would be better to use the term association rather than correlation. And again, just in case I haven't screamed about this enough, correlation does not imply causation. That failure to take into account confounding variables can cause problems. I just described the example of shoe size and test scores. Another one of my favorite examples was an early regression model that was used in World War II to try to predict the success of bombing runs, that they included various variables in the model to try to predict whether a given bombing run, whether the bombs hit the target for a given plane. And some of the results were as we would expect, that if the plane was flying at a lower elevation, then it was more likely to hit the target. If it was flying at a lower speed, it was more likely to hit the target. There were some others that turned out to be surprising. In particular, there was a strong positive correlation between fighter opposition and the success of a bombing run. In other words, the more enemy fighters that were in the air trying to kill you, the more likely your bombs were to hit the target, which at first glance seems highly counterintuitive. Well, they studied this more carefully and found that fighter opposition was just a surrogate variable for cloud cover. If it's a cloudy day, then there's less likely to be enemy fighters attacking you because they can't see you, but your bombs are less likely to hit the target because you can't see the target either. You also have to be careful of spurious associations when performing multiple tests. A famous example of this that unfortunately finally broke down a number of years ago was that for a period of like 50 years, whether or not the there was a perfect association between whether or not the Washington Redskins won their final home game the week before the presidential election. If the Washington Redskins won their home game, the incumbent party held power, and if the Washington Redskins lost their final home game, then the incumbent party got kicked out of power. And this held for over 50 years until finally in 2004 the Washington Redskins lost their final home game, but John Kerry still lost the election. But obviously, there's no association between the Washington Redskins and the results of a presidential election. Just somebody probably looked at 20 million different patterns and found that that one had worked really well for a long time, even though it was spurious. Any rate, getting to the R commands now, to calculate correlations in R, the command is called cor, C-O-R. If we find the correlation between speed and distance in the car's data, it's about 0.8, consistent with what we saw in the scatter plot. There's a very strong, approximately linear association between speed and stopping distance. And in general, in our core of x comma y, we'll compute the correlation between x and y. The only comment I have on this is make sure the elements of x and y are aligned correctly. If the rows of x and y don't match up, then obviously your correlation values will be meaningless. And we may want to make inferences about R that say we want to test the null hypothesis that R is equal to 0, or calculate a confidence interval for R. And in general, it's hard to compute the exact null distribution of R, but you can test the null hypothesis that it's equal to 0. We'll discuss how this can be done in a future lecture. Calculating a confidence interval for R in general requires bootstrapping, which is something that I no longer teach in this class. You're welcome to come talk to me if you have questions about how to do this. Things to remember from today's lecture is that correlation is a measure of the strength of the linear association between two quantitative variables, and the overall pattern is more important than the value of the correlation. Generally speaking, it's better to plot the data than just mindlessly using the value of R, because it's possible to have a very strong association, but a modest value of R. And if I haven't beat this horse to death already, correlation does not imply causation. R commands to remember: if you say plot x comma y, that'll plot a scatter plot of y against x. If you say core of x comma y, that'll compute the correlation between x and y.